This is part 1 of the combined power, heating and cooling feasibility analysis with the RETScreen Expert software. This video will give you a brief overview of the model using a combined heating and power example. The objective is to show you the basic structure of the model. There is many ways of starting a feasibility analysis with RETScreen. By clicking on feasibility or power, heating, cooling, a blank analysis is going to open. For the purpose of this video, I prefer to use the virtual energy analyzer. The VEA is going to provide me with a built-in example that I could modify as needed to fit my project. In the VEA, I am going to select for facility type, power, heating, cooling. In type, any combination of those three components is going to be offered. I am selecting combined heating and power. Then I could choose between two options, either a gas turbine in an apartment building or a reciprocating engine in a manufacturing plant. Let's choose the gas turbine. Last step will be to select my location. I am going to propose Toronto. I do not want to be very specific for the location in this example, but be aware that you could always zoom in and select the exact location of your project. By clicking on Calculate, I am asking the software to populate the entire feasibility analysis for the chosen cogeneration application, with data adjusted for the location selected, in this case, Toronto. In the location sheet, I could verify that the climate data location is in Toronto. I could then visualize my various climate information. The data of interest for a cogeneration analysis are going to be heating design temperature, air temperature, and heating degree days. The facility sheet contains some general information about the project. We are looking at a combined heating and power analysis. The VEA has automatically pasted gas turbine apartment building in the description field, and my role is now to complete with some more information such as the facility name and the address. A picture of a gas turbine unit has been also pasted by the VEA. It is possible to replace that picture with your own by clicking on the Select Image option on the top ribbon. For the benchmark section, we have decided to explain with a diagram the efficiency calculation of a cogeneration application compared to the conventional approach, which is to provide power and heating separately. When reviewing, we see that by recovering the waste heat in a cogeneration system, we could expect to reach an overall efficiency of 85, compared to a low efficiency of 42.5 when the heat resulting from the power generation is simply released as waste heat to the atmosphere. The high efficiency of 85% explains why cogeneration is often considered as a clean energy project, even though a conventional fuel may be used. The energy model sheet looks pretty simple, but when you start clicking on the various components, you will discover that it contains a lot of information. The best approach is either always to follow the steps in the ribbon or to go through the left menu from top to bottom. In step 1, system selection, the user could verify if the good project type have been selected. In this case, power and heating are selected. We are OK. We could add or remove components by clicking on the icons. For grid type, central grid is selected, because the apartment building considered is located in Toronto, where a central grid is available. It may not be always the case. Other option could be isolated grid and off-grid. In the electricity and fuel section, the user will select various fuels considered for the base case and the proposed case scenarios, which mean before and after the installation of the cogeneration project. The fuel and electricity rate are also going to be specified in this section. For our project, natural gas is selected with a proposed rate of 30 cents per cubic meter. 3 rates have been proposed in the electricity section. the electricity rate for the base case and proposed case, before and after installation of the cogeneration system, and the electricity export rate that the utility is willing to pay for the power generated by your system that you may want to export to the grid. In step 2, the heating load for the apartment building could be calculated. The main result of this calculation will be the total heat energy in megawatt hour and the total peak heating load in kilowatt. A monthly profile is going to be shown into the next section. Note that both the base case and the proposed case are going to be presented. The only difference between the two is that for the proposed case, the user is invited to introduce some energy efficiency measures in order to reduce the heating load. This is frequently a very cost-effective and good practice to consider reducing the load of a facility before the installation of a costly system such as cogeneration. In the power load and load characteristics section, the user will first enter the monthly average power load. This value could often be found using utility bills. The annual peak power load will also need to be defined. Once again, the user could consider energy efficiency measures for the proposed case to reduce the power load of the facility before the installation of a cogeneration system. This section will give you the monthly heating load as calculated into the previous section in order to also summarize all the loads for base case and for proposed case. The load characteristic graph illustrates the loads for each month of the year. The power load is in green and the heating load is in red. Now that the loads are well defined, we are ready for step 3, which is the equipment selection for the proposed case, our cogeneration system. By clicking on Power Equipment, the user could select between the available technologies for the base load and the intermediate load power systems. In this case, a gas turbine is selected for the base load. No intermediate load is selected for now. In the gas turbine form, the turbine capacity has been set to 200 kilowatt for this project. This turbine will be fueled with natural gas. The heat rate as well as the heat recovery efficiency were also entered, along with other specifications. Based on that information, the model calculates the heating capacity and the electricity that could be delivered to the load and the grid. We could conclude here that all the power generated is consumed by the apartment building with no possibility to export to the grid. For the purpose of this presentation, I will go back to the capacity and increase it, assuming that no other specification needs to be adjusted. This way, I am going to have the possibility to export some of my energy to the grid, making the demo more interesting. Note that the installed initial and O&M costs has also been defined into this section. The operating strategy section will allow me to select between 3 options: fuel power capacity output, power load following, and heating load following. In the second option, because the system operates to always follow the power load of the building, there is no possibility to export power to the grid. In the third option, we should always expect a higher efficiency. The operating profit column is highly dependent of the various rates entered previously for the fuels and electricity. In step 4, System Characteristics section, the user is not only going to be able to see a summary of the information to better understand the proposed system, but also the user will complete the selection of some secondary equipment. The first part deals with power. In this section, the peak load power system is selected as grid electricity and will provide the remaining electricity needed for the apartment building. The second part deals with heating. Again, in this section the user will specify the peak load heating system. In this case, a boiler will provide the additional heat required. Because no costs have been entered for the boiler, I assume that the existing boiler is going to be used for peak period. The system design graph could be a good tool to analyze the proposed system. For instance, you could verify from that graph that even though the capacity of the gas turbine represents only 52% of the peak power load, it is delivering almost 85% of the electricity requirement on an annual basis. The system summary table is going to summarize the technologies used, the fuel and electricity consumption, the capacity of the systems, as well as the energy delivered by each of the components of my proposed project. In the cost sheet level 1, the initial costs that have been entered into the energy models are summarized. The O&M cost as well as the fuel cost for the proposed system are also copied into the annual cost section. The base case fuel cost is also shadowed from the energy sheet, representing here an annual saving. It is a cost that I do not have to pay anymore. The emission sheet is comparing the greenhouse gas emissions for the base case and the proposed case. Since the emission factor for the grid electricity is required, the level 1 analysis uses the value included into the RETScreen internal database. The value for the province of Ontario grid electricity has been selected. The analysis shows that the project is not reducing greenhouse gas emission. In the financial analysis, the financial parameters have been automatically pasted by the VEA and the various financial indicators were calculated. From a financial point of view, this project could be considered as an unfeasible project. It has a low internal rate of return, a long simple payback period, and a negative net present value. We could easily come to the same conclusion when observing the cash flow graph. Let's see how the sensitivity and risk analysis could help our understanding of the project. The tornado graph of the risk analysis shows that the fuel costs of the base case and proposed case are the parameters that have the most impact on the financial viability of the project. It will now be wise to go back to the proper section and make sure that these costs were estimated correctly. Into the next presentation, we will go through the energy model sheet with more details. We will as well vary some of the key parameters to show the impact on the viability of the project.